Alright, so let's look at an example of a population growth model, logistic growth model. So in the example it says 10 grizzly bears were introduced to a park, national park 10 years ago. There are 23 bears in the park at the present time. The park can support a maximum of 100 bears. Assume the population of bears follows the logistic growth model. So let's break up this information. So 10 bears were introduced 10 years ago. That means the initial population is 10, right? 10 bears, and now there are 23 bears now means, so that was 10 years ago the initial population, so after 10 years population is 23, and maximum 100 bears can bear by the park. So carrying capacity here, it means, seems to be like 100, right? So capital K is 100. All right, and P naught is 10, that is the population at the beginning. So to solve this differential equation, we know capital K and P naught, so we know the solution which we derived in the previous video. So we can find this simple capital C, the constant from the integration. It's 1 minus carrying capacity over initial population. So 100 over 10 is 10, 1 minus 10 is negative 9. Okay, so we can rewrite the solution as PT is equal to carrying capacity is 100, 100 over 1, C is negative 9, so this is plus 9, okay, 1 plus 9, e to the negative simple kt. So this is the solution. Okay, let's see what is the question asked. Okay, what will be the population after 10 years from the present time? So that means present time is after 10 years. So, and after another 10 years means they are asking what is the population after 20 years, right? Okay, now one thing. We had three constants here. Carrying capacity, constant of integration, and growth and decay rate, simple K. Carrying capacity was given in the question. Constant C, we were able to find it because we derived it in the previous video. Simple K, well, we need to find it before we want to find the population after 20 years. How can we do that? Well, we know of one more condition, which is population after 10 years is 23. So let's use that. Okay, so population after 23 years or after 10 years is 23 bears, my bad. So 23 bears after 10 years, so if you substitute them, 100 over 1 plus 9 e to the negative 10k. So after 10 years, 23 population. So let's solve for k. So in the process of solving for k, let's exchange these two by cross multiplication. So we bring 1 plus 9 e to the 10k to the left and 23 to the right, so 100 over 23. So 9 e to the negative 10k, let's bring this 1 to the right, so it's 100 over 23 minus 1, so that will be like 77 over 23. Okay, so if you simplify this, okay, using common denominator 23, okay, so we get 9 e to the negative 10k is 77 over 23. So let's divide by 9. So e to the negative 10k is 77 over 23 times 9 is 207 actually. Okay, now we need to solve for k. So let's take the natural log of both sides. So if we take natural log of both sides, we get this, right? Now let's take this negative 10 times k to the in front of natural log e, okay, by logarithmic rules. So then natural log e is 1, we know it as a fact. So k is actually from here natural log 77 over 207, everything divided by negative 10. So that is capital K. Oh my bad, simple K, the growth rate. So now we know all the constants. So we know all the parts of the solution, right? So let's go back to the solution. So we know PT is equal to 100 over 1 plus 9 e to the negative kt. And we know k is natural log 77 over 207 divided by negative 10. Okay. Now then what the question asks is, what is the population after 20 years. So what do? Well, we substitute 20 for t and we know k, right? So we multiply them and we eventually substitute this into our calculator, right? So we substitute 20 for simple t and we know k, so we can use the calculator. So I think if you use the calculator, what I got in the note, it seems to be like, yes. So we substitute this into the calculator, so we get 45. So we have 45 bears after 20 years. All right. And in the question at the same time asks, what are the equilibrium solutions? So equilibrium solutions here is we have the differential equation k capital P 1 minus P over 100. So you make it equal to 0. So equilibrium should be, we know it for a fact that it should be the P is equal to 0 and the carrying capacity is the population is equal to 100. So that is one of the equilibrium solution. And it makes sense. In this environment, you can have maximum 100 bears. But if you have more than 100 bears, those bears will die, right? And it will stabilize until the 100 and nothing will change after that. But if you have less than 100 bears, the number of bears will increase up to 100, but then that's all. Okay, nothing will change after that. Okay, all right, so that's the example. Yeah, thank you very much.